Hey, so good afternoon. And today we have our webinar on geomatics, and I'm the Associate Dean of Academics in the College of Engineering at NMSU. And what we have been doing over the past few months is to create webinar series that will explain each of our 13 accredited programs. We have a lead expert faculty who will guide us through the presentation. And we also have graduates or experts that are out there practicing in their professional fields. And so today we have, as I said, geomatics. The focus is on geomatics. And it's a pleasure to introduce Professor Laksher, who will introduce the others that are here with us and go through the presentation. And so I'll turn it over to you, Dr. Laksher, and to your guests.
So hello everyone, and welcome to this webinar and introduction presentation about geomatics. We would like today to give you some ideas about what geomatics is and how it evolved in the last few, I shouldn't say last few years, because surveying was one of the very early professions that was on the earth. So we'll see now how it looks like. They started measuring with ropes, and they started measuring with very basic instruments. In the Egyptian, the Roman, the Greek, they did a lot of these interesting things to measure their land. And today the thing has changed dramatically. We see a lot of technologies today. I'd like to start with our web page here for the geomatics program. It's part of the engineering technology and surveying engineering department, and then geomatics surveying. It gives you a little bit of an introduction about what geomatics is. And then we have two cool videos here. I'm going to run the first one. Okay, so today we have an expert from the industry who's going to present about geomatics. Bob Green, one of our members of the SEAC advisory board, that's the advisory board that sets our educational objective that tells us how the program should grow, what the industry needs, and then we reflect that in our curriculum, we reflect that in our teaching, like what equipment, for example, should we be teaching the new generation. So Bob Green is going to talk about this today. Bob is licensed in Colorado, and he has a lot of years of experience in different parts in surveying and geomatics. So welcome, Bob, and it's all yours now. So I'm going to stop sharing here and try to figure out what the problem with this video is.
Okay, can you see my screen?
Yes, I can.
Yes.
Okay. Again, I'm Bob Green, and as Dr. Alexer said, I've served 2 terms, which is being extended because of COVID. So I'm in my 7th year helping out at the university. And it's been a real transitional period for us. So as you noticed at the bottom left, survey engineering is included because the original name of the program was survey engineering, and now the term geomatics. So with that said, let me get going. The agenda today and what I'm going to talk about to begin with is, what is geomatics? What does it mean? What does it do for me? How is it used in industry? Then we're going to look at several tiers of geomatics, which there's many tiers. The first one is going to be land surveying. So that is probably the biggest focus of the program, is to create licensed land surveyors. And when we're looking at land surveying, and I'll show the changes that have happened over the years, we're looking at both geodesy and GNSS satellite technology. And that's kind of important to know, because how it operates definitely affects everything we do. I mean, we have GPS now in our vehicles. You know, back in the 90s, it was called the next utility, and it surely has become that, and has become a tool for measurement professionals around the globe. We're going to look at robots, robotic total stations that take antiquated technology and incorporate high-level mechanics. And you'll see that I have a video here that I'll show you on kind of how that works. We're also going to look at deliverables that we can get out of our field work through CAD drafting and 3D modeling. The survey program has some of these platforms, and I'll kind of point that out as I go through my presentation. Another thing I'm going to focus on this talk is remote sensing, because that has become a dominant force moving the industry forward. And we're going to look at drone technology, both photogrammetry and Lidar. There's also emerging markets in thermal inspection and gas sensors, so to go into a gas field and inspect it before you enter it with a drone. So those are some emerging technologies. And we're going to look a little bit at terrestrial 3D scanning as well, so that we're generating our point cloud not from a drone, but on the ground. And I'll show different ways that we can accomplish that, and different technology that is involved. Another emerging market is monitoring and change detection. So, to get a position, say, of a dam, and then every month you go out and you take new measurements on that dam to see if it's moving. We can generate velocity reports, send out data to emergency response. All that is part of geomatics. So first of all, let's understand what the term means. So geo is for Greek Latin for earth, or taking a derivative of geography, just like in geometry, earth measurement. So this is earth matics, and matics being a collection of information and data collecting it physically in the field, processing that data, then analyzing the data, and usually to create a deliverable. And then the storage of that is very important for generations to come. I mean, every time you go out and survey, you don't want to have to rebuild the watch. So instead of storing it with rolled up plats like we used to do back in the 70s before computers, we're actually storing it electronically for easy retrieval. So, geo, again, the term geometry is one that kind of it's always fascinated me. Earth measurement. I could actually do a class on just that term and how that geometry impacts geomatics, where they kind of run side by side. So naturally, in order to get a geomatics degree, you have to be very good at geography, trigonometry, and so on. So I started surveying with my dad. I'm a third generation surveyor, well, kind of like 2.5 generation surveyor. And I started in 1973 when I was a young teenager. And he had a K&E Mountain Transit, kind of a relatively close to the one pictured there on the far left. He had a Philly rod, like the picture there, with the rod with the red and white target on it. And he didn't have the bottom right one. I used that when I went to work for Boston Survey Consultants. The BSC group is what they're now called, out of Boston, Massachusetts. And that was a plane table and an alidade. So we really created our deliverable almost in the field. And then it was on a Mylar piece of paper, document. And then that would be taken into the office, laid on a light table, and then really a drafting artist. I mean, these guys were so skilled with freehanding, and they'd freehand contours and line work, and it was really a craft that was involved. Now you look at today, and this is all the changes that I've been through in my career. I remember it was 1978, the summer, I can't remember the month, and we had just started launching satellites in February of 1978. So I was a young intern, and I was sitting, we were doing percolation tests, I remember. That's how well it's ingrained in my head. So we were doing percolation tests for septic system design. And then after we did the test, we would locate them with the instrument there on the far left and the rod with the target on it. That's how we located them. It was called transit and stadia observations. And I'm sitting on the ground eating a sandwich at lunch, and our boss came in from the mother office in Boston. And he told me, he said, "You know what, Bob?" He said, "There's going to be a day when you can take a magic black box and you can put it on the surface of the earth, and it will tell you where you are, X, Y, and Z." Now, that was hard for my young teenage self to wrap my mind around, because I was out there using the equipment on the left, and you're telling me that magic's going to happen. We're going to put some form of receiver on the earth, and I'm going to know X, Y, and Z where I'm at. Well, that day has finally come, and it does exist. It is happening as we speak. And today, I went from using this old antiquated equipment to shown there is I think it's an R12 GNSS receiver. And I'll talk a little bit more about the technology inside of that unit. To drones. Part of the reason I'm up in Wyoming is we are flying a mine, and we're doing some both Lidar and photogrammetry and inspection work up on the mine. And then to the bottom left of that 2020 group is a total station, robotic total station. The university, the geomatics program has one very similar to that. Making what I used to do on the left now automated with electronics. And then to the far right, or bottom right, is a Faro scanner. The program has that pretty close to that same scanner to make 3D renderings from point clouds. 3D rendering from point cloud can be made from the drone as well. So there's lots of ways to incorporate this data. But the science is getting all of this data, which is really great, but then having to merge it. And then how much of it do I actually need? And communication with my customer of what his needs are. So communication doesn't really leave because we have technology. It actually increases the need because we have so much data that we need to know what to do with it all. So the Geomatics program really sets one up to enter these various fields. We have people that work for us, their full-time job is flying a drone. My problem with them is they are more concerned about 2 thumbs on a joystick than an index finger on a calculator. So I'm trying to teach them the transition to take their technology of what they love to do, of fly drones, and apply it to geomatics and surveying. Deliverables, whether it's old school or new school, is to give our customer usually data that ends up on a 2D deliverable. Now that is changing, dramatically changing, because once you give an architect 3D data that we're going to be looking at here shortly, that guy never wants to go look at black lines on a white piece of paper ever again. So the demand for geomatics professionals is just going to keep going up and up. It's not a dead market. I believe, and Dr. Alexia could correct me if I'm wrong, but every single person who graduates from the Geomatics program, when they get out, guess what? They got a job. And so, and a good paying job at that. So it's a career that keeps one busy. You don't have to be stagnant because there's so much opportunity.
Can I interrupt, Bob, and just give a quick comment about this?
Yes.
In fact, we have a reversed problem in geomatics. So we do get a lot of emails, a lot of phone calls, and companies, firms, agencies are looking for surveyors, are looking for new graduates. Do you guys have any new graduates? So it's really interesting that the amount of jobs that are being created in geomatics is much more bigger than the amount of graduates, and that's nationwide. We just have NGS. NGS is the National Geodetic Survey, and they have few of their old geodesists that are retiring. They are looking for new generation to come in, and the demand there is very high. Same thing in just land surveying, same thing. A lot of surveyors now are retiring, and there is a lot of demand for photogrammetry. So we actually have an interesting problem is the market is full of jobs. So graduates can pick and choose. We had one graduate last semester, he got 3 offers, and every time I asked him, did you already sign a contract? He said, no, I'm still thinking, which one should I go with? So a lot of jobs. So thank you, Bob.
Yes, and it's a growing profession. It's not shrinking. Now, the need for actual physical land surveyors, people that go out and put in property corners or survey boundary, that kind of stays about stagnant. But the big umbrella of geomatics is just, it's going crazy. So what we're looking at here, Dr. Alexia had mentioned earlier that there was a day back in the mid 80s that there was just GPS. GPS was the only satellite constellation. And then the Russian government got wind of it, and they wanted their own constellation, and that's called GLONASS. And what we're looking at here now is a display from the receiver. So on the far left, upper left, you can see this receiver that I had before that I take out in the field with me. And it actually has a built-in web UI so that with my cell phone, I can tap into that web UI or with my controller or whatever, and I can track satellites around the globe. Now, if that isn't cool stuff, tell me what is. You can actually see what is happening. Now, they communicate with you you don't communicate with them. It's kind of like being married, you know. So it's a one-way communication. So we really don't. There have been a couple rare instances where I have actually interfaced with satellites. I did some work on consulting for the Air Force on all the ground-based telemetry stations for the Space Command, and I went to all of the United States facilities where they track satellites, ground-based installations, and they encase these dishes on these Air Force bases in this canvas so that our enemies can't see which way we're pointing them. And I was in the same bunker as the atomic clock. So I've done I've had some pretty cool experiences, but any person can see this that owns one of these receivers. And you can see the term from GPS, when it was GPS, is Navstar. That is our constellation, the satellites owned and operated by the US government and really operated by the Air Force and the Coast Guard primarily. And then there's a Sbas Satellites. Those are fairly new as well. They're satellites that are correction-based. So they're owned by, at least in the United States, they're owned by the FAA, and these satellites help planes get more accurate positions upon landing so that they can better line up with the center stripe on the runway than they could pre this Sbas, or satellite-based augmentation system, which in the United States we call WAAS, or wide area augmentation. And then Russian GLONASS, European Galileo is still in production, and they're still launching satellites. They've learned a lot from our mistakes, so it's a very quality constellation. I'm not saying ours isn't, but they learned a lot from us. Beidou is Chinese. They just finished their constellation right in the middle of the pandemic. I think it was May. They launched, I think it's 37 satellites in their constellation. Some are geostationary and others are inclined geosynchronous. Then QZSS, or Quasi-Zenith, is a figure-8 constellation over Japan and Australia. We really don't usually see too many of them satellites in our hemisphere. And then the Indian Regional Navigation Satellite System, owned by the country of India. And the other cool thing that's going on here too is, I don't know if it's really good or bad, it's kind of maybe somewhere in the middle, but back in the day when GLONASS was kind of competing with GPS, GLONASS was anti-GPS. The only thing we had in common was 24 satellites completed a constellation. Other than that, we were their frequency division, multiple access, or code division, we were totally different. Now, most of these constellations have frequencies and data in common. And our new satellites that we're launching, I think we got 3 of them up now, GPS-3. I'll talk a little bit more about that here coming up. So not only can I see that, but I can also see what's predicted. And anybody who started out with GPS, when we were lucky to have 5 to 6 satellites, during the day, the green line up above says we're going to hit a maximum of 41 satellites with all of this data. We average down at the bottom there 34.5 satellites throughout this time period. It's just amazing to me, you know, having had been started out at the infancy of GPS back in the mid 1980s to now seeing what it has become. And actually, sometimes we get too many satellites, so that the manufacturers have now gave us utilities where we can filter out and only accept the good data. So for instance, you're standing underneath a tree, for instance. Well, there's going to be noise generated, just like a radio signal. There's going to be noise, RMS. And that noise we can filter out, and we can then start dwindling the number of satellites because it just gets to be too much data. Here I have a little video that kind of shows the robotic portion of what a robot does, how it measures, automatically moves for us. I don't know if you'll be able to hear the audio or what, but I'll give it a whirl here. So that's kind of a brief run through of a robot. This technology's really been around for about 20 years. It was very crude at first, but a survey crew back in when I started out was 3 to 4 men. And you'd have a rear chainman, a head chainman, a rod man, instrument man, and crew chief. So it was actually called a survey party because it was just so many people to get the task done. And today, as you can see, there's nobody behind that instrument. It's a one-man operation, although I prefer to have 2 men because for safety reasons, you should have 2, but nonetheless, pretty impressive stuff. Okay, so did I end up at the right place here? Yes, I did. I do a lot of research and I do a lot of lecturing for my company, and some of the Apollo missions left these, what you see here on the left, that is called a retroreflector. And it was left on the moon, and it's a series of prisms so that we can take ground-based measurements to the moon. And one thing this retroreflector has taught us is that the moon is moving away from the Earth at about 4 centimeters per year, and well over a meter since we have been monitoring it. And from this science, this retroreflector science, we've learned a lot. So guess what we're doing now with our new Block 3 satellites? We have this new generation of retroreflectors that are going to go on these units, so we can measure to the satellite. And that's going to have huge impacts on the industry. Now, you won't see those impacts till 2024, 2025, but it's going to lead to some incredible science. So we learned from the past, from these retroreflectors left by several of the Apollo missions. And if you look real close at that picture, you can see a shoe print there that's still there from the original people that placed that on the moon. And now we're going to look at some drone technology or remote sensing. Remote sensing is a whole industry itself, so it ties into geomatics very well. But I work with 2 individuals. They have one has a master's degree in remote sensing. I think he got his master's at the University of Hawaii or something. But anyways, there is a whole industry relative to remotely collecting data. And none of this, when I first started out, was available. So to the upper left, we have a fixed wing photogrammetry drone, meaning it has an onboard camera. Photogrammetry does not give us really ground-based measurements, but we use intersecting pixel technology. Then we have a couple of drones up there, equipped. One is equipped with cameras. They're kind of off to the right. And then we have a VTOL. The big one in the middle is called a Tron, and the one right kind of below it is called a Trinity. And these are VTOLs, vertical takeoff and landing. So the drones in the upper right, those are copters. And they're great to go up in narrow spaces because they'll go straight vertically up, and then they'll start their mission that you plan. The issue is with battery life, and they're just really for smaller type of projects. They're not for very large projects. Where these VTOLs, the UX-11 there on the upper left, that is not a VTOL. So you have to kind of toss it like a frisbee almost, and so it takes off, but it needs a lot of room. Where these VTOLs, and I'll show you here a little video in a second, how they take off, and where they take off like a copter, and then they move forward and complete the mission. These are Lidar sensors. Everything we looked at before was taking pictures. These units do not so much take pictures as they create point cloud from physical Lidar measurements. And the Lidar is getting really good these days. And the benefit to Lidar is penetration through canopy, through trees. So they have a series of echoes, so they can hit a leaf or a branch or whatever, and then penetrate all the way to the ground to give us a really good idea of what the ground is doing in that thick, dense vegetation. The one to the left is a Green Valley kind of entry-level unit. The VX-20 does about 600,000 points per second while it's flying. And then the yellow scan surveyor to the right is about 6,000, and the VX-20 is more like 100,000 points per second. So you fly it a little bit slower, but really cool technology, and they all bolt as what we call payload in the industry. Naturally, if you're using any of these, you can't use a little toy to bring it up. These are fairly robust drones. And this kind of shows the camera technology that we interface with. Again, depending on what you want, we actually have thermal cameras that do inspection. That's real popular on mines for finding stress points in this big heavy machinery. They have these drag lines that are under constant stress, where we can go in there with drones and inspect them. They have conveyors that we can inspect, all that kind of good stuff. Here's another video. I hope it doesn't go wonky like my last one, but this is a Trinity unit, and I'll show you kind of how it takes off. It is amazing that it's able to go up vertically, and then it pauses for a second, and the whole propeller system rotates, and then it takes off and goes horizontally. Probably not the best video or as far as quality, but it does definitely show what these things can do. And so we usually do a takeoff off of a hard surface. And it'll go to its programmed altitude, to its programmed flight pattern, and boom, off it goes. Now that's some pretty cool stuff. I don't care who you are right there. That's some pretty exciting stuff. Now we're going to look at terrestrial LiDAR. These are the guy that I told you about that has a master's degree in remote sensing. He operates one of these. There's only 14 in the world, and my company is fortunate enough to have one. It's called an MX9, and it creates giant point clouds while driving up to about 50 miles per hour. So we can collect a lot of point cloud data, and then that data can be taken in and looked at by engineers and surveyors and designers. It's really good if you drive a little bit slower too, because it has a camera on it as well. looking for cracks in the pavement, all that kind of stuff it can do. Nathan just finished a project up in Alaska, about 500 miles he drove with this unit. And he went both directions, so it was like 250 and 250, I believe. But this is another emerging market. These units are going to get smaller, more lightweight. You're looking at $750,000 right there. So that's why not many people have them. But that price will come down, and the technology will get even better. When I looked at buying, when we went to buy a first GPS system back in the 80s, one receiver was a $100,000 investment. You needed 3 plus software. You were in it for $500,000 just to get started in GPS back in those days. And now we pay a fraction of the price for 10, 20 times the technology. So here we're now going to take a peek at the data that came off of that unit. So you can see this is all dense point cloud data. Each one of those individual points has a given X, a Y, and a Z. And so we can take that data and we can utilize it in multiple ways. We now have software that is just really starting to get fine-tuned that will remove all the vegetation. We'll put different entities into different layers automatically for you. So if all you wanted was roadway, all you would see would be roadway. If all you wanted was ground, you would see ground. If you just wanted buildings and fences, they're all put in separate categories with the press of a button, and on an average project, 3 to 5 minutes of processing. Just simply amazing. There is one at the Geomatics program, very similar to that one. And you can see how much benefit it would be to these plants and facilities. And there's what's called BIM going on right now, building information modeling, where you can have a whole business of just going inside of factories and buildings and letting staff there know where all the electric outlets are, where all the piping is. And like, for instance, if that valve in the picture there broke, that I'd have 3D data that I could construct a model and send it to the manufacturer for redesign. All these things are up and coming. And so the one in the center there, the SX10, that is both a total station, like we looked at in the one video, and it is also a scanner. Does about 26,000 points per second. Plus, so you could be scanning a bridge for design or one day, using it to lay out a building the following day, and setting somebody's property corner the next day. So it's kind of a one-size-fits-all field to finish unit. These photos I took because it kind of, the one in the upper left is taking that rich 3D point cloud data, but your customer wants that 2D deliverable still. Now that's going to change. But right now they say, well, all I want to know is, you know, where the curbing is, where the gutters are. And this shows that we can ID points from that point cloud and create an old school type survey from high-tech technology. So that's why I included that one. The one in the middle is actually the Idaho State Capitol. It was a job that we were hired to scan. And believe it or not, that is not a picture. That is colorized point cloud data. So it's taking the 3D data like we have on the upper left, but then applying photos to it. And then each pixel or each point in the cloud gets assigned a color. And so that really isn't a picture. That is actually data, mathematical data. The bottom left is the inside of a parking garage that was actually scanned for floor flatness. There was some issues there going on, and they were hoping that they weren't going to have to take part of the parking garage down. So even though it was just the floor we were concerned about, we did get full 3D data of the ceiling as well. And we have now floor flatness utilities. So you can go in there and you can tell if something is flat, if it's level, a whole bunch of different things that are coming out of this technology. now we'll talk about subterranean. This is a picture of from CNN. Anderson Cooper got sent down into a cartel drug tunnel. Bob Green, yours truly, was also sent down into that same cartel drug tunnel underneath the Mexican border between Chula Vista, California into Tijuana. I went down there and I made a 3D model of that tunnel. Not so much, that was a tram that went from Mexico inside of a convenience store where they cut out the bathroom floor and put it on a hydraulic lift. And that's how they hid what they were doing. But we made a 3D model of it for volumetrics. Number one, some of it was going to be filled with concrete. And number two, that they put a manhole down in there later on once it was closed up. And they bring dignitaries and stuff down in there to show Border Patrol what's going on. So my customer was actually the Army Corps of Engineers and Border Patrol Intelligence. But that was a pretty cool project. So when I think geo, I think Earth, but it's not on the surface of the Earth. This is subterranean, and tunnels now are big in the industry. We have entire platforms that just focus on the building maintenance of tunnels. This, I thought I'd show a non-traditional job that I did. This is a interferometer vacuum telescope that I helped lay out. The reason I got involved is they needed sub 2 millimeter accurate positioning. And the problem was half the telescope, there's actually 5 of these collinear pipes there, was outside. A portion of it was inside, but not temperature controlled. And then a portion of it was temperature controlled. So to meet 2 millimeter requirement, a couple people had tried. I got a call, said, do you think you could do this? I did. And so I laid out that telescope there. And it's out west of Socorro, New Mexico. It was a joint venture between New Mexico Tech and the United States Air Force. And this, it was kind of funny. It's called an interferometer vacuum telescope. So in true government fashion, they built the telescope and then they realized that they didn't have a vacuum big enough for it. So they had to kind of reverse engineer the whole project. So that is, one wouldn't even think of something like that. I also did a lunar laser telescope where I aligned it with the moon for NASA over at the Johnson Space Center, right there outside Las Cruces. It was a lunar laser telescope encased in an Astro Haven facility. That science, it was kind of funny to actually get a call from NASA. That was just kind of bizarre, but anyways, that's a story for another day. But that was a very cool project. And these are all things that when you get out of your program, think that you're just going to be doing land surveying. You can customize your career whichever way you want to. And I thank you for your time and attention. And if anybody has any questions or anything, I'd be more than happy to answer them.
Well, that's excellent, Bob. And I just wanted to make one comment, and then we'll open it up certainly to the audience here. But you have all this point data in XYZ, right? And
yes.
So you have the beginnings for holograms, so you can hologram a lot of stuff as
You
well.
bet.
Project it out.
Absolutely, you can. And that's a whole nother market. I mean, this stuff going into the movie industry, and then perpetual documentation. I mean, you know where everything is. With a click of a button, you can get an X, a Y, and a Z, not only spatially of where you are in the room, but geospatially to where you are in the world. So I could pick one of those small points, and I could tell you where that coordinate sits within the globe. And that, when I did the tunnel, I did a lecture with this U.S. Secret Service, and kind of teamed up on this lecture. And people in the room were spatial people, and they totally understood how I scanned the inside of the tunnel. What they didn't understand, and what you will learn in the Geomatics program, is how to take that data and put it where in the world it belongs. And that's the difference.
That's incredible. Okay, so yeah, I'll turn it over to you and Dr. Lecture to field any questions from the students who have logged in.
I would like, if there is time, to give a little bit of an overview about the program, if that's possible. Will it be okay? We start with this. I think now I know what the problem was, and hopefully the web page will work. And if that's possible, I'd like to go back, introduce the program itself, and then we can take the questions at the end, or it's up
Yeah,
to you. Or
that sounds good.
okay, so let me go to the web page, and you can see my web page now, or you can see my screen now, right?
Yep.
So the National Council of Engineering, Education and Surveying has a yearly award that gives to the best schools in nationwide. And we were fortunate at, well, 2020, it didn't run, just to let you know, COVID, okay? But we were fortunate in 2019 to be the grand prize winners. So right now, because, well, I'm sure we were going to win it again, but right now we are still the grand prize winner. So we are still the best surveying education program nationwide. And then there are other schools, of course. One of the reasons our program did win that is the way we structure our curriculum. So back to what geomatics is. I think Bob said everything about geomatics. It's mainly how to make accurate measurements that are needed in every field. Any field that, any engineering field, or even agriculture, or a lot of fields. I think Bob mentioned most or some of these fields, but there are a lot of fields that you will need precise measurement. And that's where geomatics will come in. Here are some of the different tools we use, different applications we are doing, and you can see we use a lot of technologies, and we use satellites, everything. So career paths, a lot of job opportunities. Again, we have a reversed problem. We have more jobs than graduates nationwide. The technology is emerging, and it's not a button pushing. So that's not what we are looking for. All these tools, all these technologies, we don't want just people to press a button. We want people who know how to use the technology, know its limitations, know which one to use. You can use GPS in certain locations. You cannot use it in other locations. Very simple example, if you take a GPS receiver in a downtown where you have these very tall buildings and you expect it's going to give you the correct location, wrong, it's not going to. If you take it in a canopy or in a forestry and try to get signal, it's not going to get that to you. So each equipment will have its own limitation, and this is where our graduates are going to be expert in, which equipment you use, how to integrate these equipments, and that's why the market is full of jobs. They need qualified people to do that. The job market has different names for our surveying professions, cartographers. You can be a crew chief, geospatial data analyst, of course, land surveyor, land surveying, surveying engineer, Lidar analyst, photogrammetrists, surveyors, geodesists, a lot of different fields you can do. Some of the employers that we have B&H, we have BLM, the city of Las Cruces, the county. And again, when I say the city or the county, any city, any county, regardless of your location. National Geodetic Survey, National Geospatial Intelligence, NGA, that's also, we have some graduates there. Any DOT department, they need surveyors to survey the roads, to survey the infrastructure. So a lot of, these are just examples here. And then you can also start your own firm. Now I'd like to talk a little bit about our curriculum here. So we have an interesting curriculum. Our curriculum, if I will show it to you here, looks like this. Now, we have what we call two different paths. You can start your education for the surveying or for the geomatics program at NMSU. So you will be a freshman, and then you will take all the different courses, sophomore, and then you proceed to the surveying curriculum. That's one way. The other way is transfer students. And that's why when you look at our program, we do call it a +2 program. So that's another way to get to our program. You do your first 2 years. These first 2 years are most likely going to be the general education, math and physics, and some introductory courses, computer programming, CAD, drafting, GIS, and then come to our program where we will teach you more about the geomatics, about the different aspects of geomatics. We will teach you about photogrammetry, we'll teach you about geodesy, we'll teach you different courses about the boundary law, we'll teach you the GNSS positioning, we'll teach you a lot of emerging technologies. We'll try to cover different ones in different weeks. And then you will do a senior project, which I would like to show you here, some of our students when they were doing their senior project, which is really interesting. So I'm going to jump to this part here. So this is one of the students here doing a senior project using the S10. Here is another interesting senior project. They wanted to map all the trails in the city here. So we had a student who had the GPS antenna on her bike, and then she drove these trails and made a nice map. Traditional GPS units for topographic mapping, another project. This is a demo here where students were seeing the mobile mapping, laser scanners. So our students really do most of the different applications, most of the different areas in land surveying in their senior project. It depends, like this year, our students are interested in integrating drone data with laser scanning data. So that's what they are planning to do for their senior project this year. So a lot of different things that you can do here. So the most important thing about our program, it's online. So once you have your first 2 years, some of our students, once they finish at a community college or a 2-year, they will decide, well, I have a job I would like to work. Is it possible to still get the education? Why is the education important? Most of the states now, including New Mexico, do require a 4-year degree to get your license. Once you get your license, you are on a completely different pay scale. Your road to grow, to progress, to make your own company, to maybe triple your salary. Maybe Bob can correct me on that. Once you get your license, you are on a completely different track. So most of the states will require a 4-year degree to get your license. So you can do the junior and senior years online. And we do have students on different paces. Some students will say, well, I'd like to take 2 courses per semester, or 3, maybe 2 and 1 in the general education. So that's a very important thing. And that really ties very well with what NCEES were looking for. They were looking for a curriculum that can be easily delivered. Easily here doesn't mean that the content will be easy, but students can have face-to-face options, that's what we have, or have the other option online. So the point, our program is online. You can take these courses online. We do have ways to facilitate that. We do have ways where we can have the students like come on weekends to do their labs, or can do their labs under a mentor. A lot of things that they can do with the online programming. So I think I covered the part I would like to cover. If there are any questions, I will be happy to take them, and maybe we can open the floor now to questions to Bob and myself. So I'm going to stop sharing here.
We had a question about Bob's contact information, so I shared your LinkedIn page, Bob.
Yep.
in that. I don't know if you wanted to give any other information as well.
No, I think LinkedIn is a great way to stay in touch. I'm not real super active on it. I mean, I just get so busy. You know, like right now I'm in Wyoming, and who knows where. That's kind of what's nice. I don't really know where I'm going next. Wherever my assignment lands, that's where I'll go. And so it's just very interesting. I'm really pleased to be a part of this conversation, and I will perpetually be helping out with the program, lecturing whenever I can. I've already done it several times for Dr. Alexia, and back when Dr. Frank was there, and for Dr. Worm. So it was my pleasure to help out today.
So Bob, maybe I'll ask then if no questions are coming. How, I was just saying, once you get your license, you are on a completely different path to grow. So can you elaborate a little bit on that?
Yeah, I think.
Why do you need the license, and how does it really grow you, and the effect of having a license?
Yeah, if you want to be a land surveyor, definitely there is a pay scale increase once you become a professional land surveyor. There's no doubt about that. However, it's something to keep in mind that you don't necessarily have to get licensed, as some people don't wish to. They don't want the liability, for instance. So instead of doing that, they'll go into the remote sensing portion, or maybe they like construction, because that's a whole nother market. Dr. Alexia had a slide there showing it, but construction is a big market. And our infrastructure, you know, our highway system was built in the 60s. And so it's now needs to be repaired and modernized, and taking this 3D rich data and being able to collect it, share it with engineers and architects, and be a part of the solution, not the problem, is just amazing. Every day I wake up and I'm just so lucky to have a job where, you know, we get to help, where, you know, part of our job as a licensed land surveyor is to work in the public good. And that's what we do every day. Try to take the best measurements that we can, apply the technology, and Dr. Alexia hit it right on the head. In the industry, there are what we call button pressers. They think it's all magic. And once you know the science and the mathematics behind the magic, that's where the dollar signs come in. So I think I would agree with Dr. Alexia.
I think we had a question from Nike.
Hi, nice to meet you all. Actually, my major is in aerospace and mechanics, but I always like to know more about everything, pretty much. Like I work in IT, nothing to do, with my with my career, but I like to learn different things. One of the things that I like to observe is that I read an article that it was about how they found the Mayan civilization that was hiding in Guatemala. So pretty much they use this kind of equipment, actually to find it, because it was like very, very deep into the how do you say that? I don't know. That's the translation. I'm sorry about that. But one of my questions is that right now I'm like working in a project that is gonna start like for water resources. So pretty much I work for them. And my question is, what kind of research, could be done with this kind of equipment and everything, like to find solutions water-wise, like about water resources here in New Mexico and the places, around, because that could be, very good data, like to add to that specific research. And I think, like, because the kind of soils and things like that, it can be found, right?
Yes. A matter of fact, a couple of years ago, I did a job in conjunction with Cochiti Pueblo, one of the reservations. And what they were using the technology for, what I was helping them with, is they were trying to prove that the Indians planted corn before a particular time in history. And I don't remember all the ins and outs of why that was. But with this technology, we could see depressions in the ground where there were channels where water was able to, some form of crude irrigation ditches. So yes, it can be used for that. Can also be used to, especially on the big scale with Lidar mapping, to make contour maps and look for drainage and anomalies and what slows that down and what you can do to speed it up. And just nothing else but inspection, so that when we have floods, there was a big flood in Doñana County about 15 years ago or so, and the city of Hatch was totally underwater because a dam broke. And so we can use the monitoring technology. We sell a series of sensors made by a company called Sensive. They're $500 sensors or so that can be placed on the dam, and then that information of movement goes seamlessly to the cloud. You set movement and velocity thresholds. Once those are exceeded, we can save the water or save the community from the water by letting them know ahead of time before that's going to happen. So water is definitely part of the plan.
Great.
So if I can, oh, I'm sorry. Yeah, finish.
No, go ahead. No, I had another question, but if it's
okay,
like
no, just related to applications of geomatics or these nice technologies in water, different water and applications. So I mean, since you were talking about research, this is one of the articles I did a few years ago. It's about extracting shorelines from our data. And you see here the word spatiotemporal data. So we had, if you scroll down just quickly here, we had what we called a digital elevation model. And then we had the bathymetry data, which mapped the seabed. So you have above the sea surface, that's the shore part, and that's the sea part. And then we have our nice ways of predicting the water level. That's not my area, but again, collaborating with another scientist. So they were able to get the water surface here. And then we in geomatics were able to, and again, I'm just talking about it quickly here, we were in geomatics were able to integrate both the digital elevation model and the bathymetry data to get what we call the CTM, coastal terrain model, which is all the terrain continuing underneath the water surface. And then we had these nice water surfaces, and then we can intersect them and then create some nice shorelines. And we can do this at different times, so we can see how the shorelines or how the water is changing. That's one application. Another application, we use GPS in monitoring water wells. So the height of water wells in different wells, and then they create the whole water basin. That's another research part. And if you just searched geospatial applications in water conservation or geospatial application, geomatics application, GNSS, GPS, photogrammetry, you will see a lot of other researchers that are doing a lot of things similar and maybe more advanced using geospatial applications in such things. I just wanted to give a comment when you were saying you are majoring or you are in aerospace and have an IT background. And that's really very interesting, because if you look at geomatics, we use both. So we have a lot of, like today I was teaching GNSS and I had to go over the mechanics of the satellite. How do we set the satellite in the orbit, and then the orbital parameter for the satellite, all of these different things. So that's part of the aerospace field. And then we also have the other piece, which, as Bob was saying, you get all of this data. So how are you going to handle that? We give it, or we will say we'll collaborate with IT people and researchers on handling this giant data set. So Geomatics really have both hands. Drones will get the aerospace part, plus also you get the data. So how are you going to do the feature extraction, for example? How are you going to extract features and buildings and all of that? So I'm sorry, maybe I interrupted your other question, but go ahead.
Oh, no, no, sorry. Actually, that's very interesting. I'm sorry about that. I was like just amazed about that. Sorry. Well, my other question was, because I don't want to take, you know, much of the time, because I know that other people will have questions, but on 2011 and 2012, I was able to participate with NASA to send, you know, my experiment into the International Space Station. And I actually was able to do a research on the effects of microgravity in water purification with the use of cactus mucilage to actually be able to purify water from heavy metals. So one of the things that I got like connected right now is when you actually show the picture, Mr. Bob, the picture with the radar that you had over there. And another thing that one of the space researchers said about the water that moves, you know, like from one place to other in the moon, and it has like a surface for 15 centimeters. Mm-hmm. So that was like something very interesting to know how they actually can, you know, measure that movement with those things that they have in space.
Yeah, those retro reflectors have given us some really quality data. And the Lunar rover actually had a wheel fall off. I don't know if you know that, but it had one of its wheels fall off. And what they did is they decided to keep using it. And because now, instead of a smooth, you know, course on Mars, where the rover is at, they were able to detect that there was actually water on Mars, right, by a mistake made by that the Mars rover. So it's kind of funny how you happen upon something by chance, and it's the same thing in our industry. I mean, I'm figuring out some stuff that the manufacturer didn't realize that we could do. So then my company can then capitalize on selling that product, right? So it's you know, kind of like there used to be an ad for a company called BASF. We don't make the things you buy, we make the things you buy better. Well, that's kind of our interface in geomatics, being professionals and giving feedback to manufacturers to look for the perfect solution for that measurement puzzle.
Yeah, we have another question here from Jericho at the chat. And it's, how do you see the future of geomatics technology as a driving force in effective urban planning in developing cities around the world?
Can I start with this part, Bob?
Yeah, go ahead.
Okay. And the reason I would like to start is interesting because actually, well, I do have some, let me go back and do a share, some nice things to show here. So this is actually a developing country. It's in Egypt. And this project here that we were doing was using, so I first would like to show what technologies we were using. We were using the laser DEMs, and I think we learned a little bit about lasers today, and Iconos, which is a satellite imagery. So what we did here is we had the laser point cloud, and then I don't want really to go in the research part, but I want to show the application and why is it important. So what we had is we had the laser, and the laser doesn't really show you, this is the laser here. It doesn't really show you anything except the heights. So these are heights. What you see here are heights. And you see here a big change in the color going from very dark to very bright here, and that's because we have a cliff here. And that was causing a lot of landslide. It was causing, in a developing city, a developing country, it was really causing a lot of problems. And I think in 2009, there was a big landslide and a lot of people were injured and even some died. So what they were looking for, okay, how can we handle this thing? How severe is this part of the cliff? So what we did here is we got a satellite imagery. Now you can see the cliff. Now you can see there are houses down here. Maybe the resolution is not that good because it's just the PDF file, but you can see that there is an issue here. And what we did here is did some research, integrated this and this, and then we provided them with a 3D model for the area. You see the cliff here, and we gave it to the planners. Well, we are not urban planners, but we gave them the product. And that's what I usually will say about geomatics. We are here to solve problems, but you have to define the problem. What do you need from us? So they were looking for what they call 1 to 5,000 topographic map. Can you guys in geomatics give us this type of maps in 3D? So we as planners can start looking, what can we do here? I don't know what they would be doing, of course. That's the urban planner part. But what we provided them is this type of output. We had different options. This is where really the research part, this is really where you need the education, because you can just say, well, I'm going to use an image here. I can use the satellite image. Well, the satellite image is not going to give you the height. Well, I can use just the DEM. Well, the DEM is not going to show you where the buildings are, all of this. So that's a good integration application, and taking what we can call, if Bob will agree with me on that, the raw data, meaning the images, the lasers, the laser point cloud, integrate them, do our research, and then assess the final quality. Once we have a good quality that fits the client requirement, then we give it to the client, and this is what we will have. Another thing also, this is not really a developing country, but this is, I think, in Maryland, another piece of research. They wanted this part here. They want to do a 3D map of this part. They wanted to count the buildings, areas, the shoreline, the roads, Well, you can give it to someone here and they will start just measuring. That will take them forever. So what can we do? Well, we can get a satellite image here. That's an image. And then we can, in this piece here, what we did is did some of the research, about how to integrate data, how to do the feature extraction. And then at the end, we were able to extract the roads, give it to the urban planners. And I think you will see here also the buildings somewhere. If I just did it this way, yes, here it is. And then they can integrate where the buildings are, where the roads are, although it's not an developing countries, but you can take this raw data and start doing your urban planning. Another one is this one here, extracting the buildings. So in conclusion, or answering your question, yes, if you just, again, do a quick search, geospatial application in urban planning, you will see a lot of applications. You will see a lot of interesting things. You take the raw data, integrate it, and then provide the client with, which are going to be the urban planners here, with what they would like. Bob, would you like to add something?
Yeah, I mean, I think technology, when it comes to urban areas, has really, it's really sped up processes, right? So, and safety. So for instance, pre-technology, if I wanted to locate or know the coordinate values of a manhole at the center of an intersection, I had to walk out in that intersection. I had to look over my shoulders. It was dangerous. Today, everything is done remotely. So we at maximum, we may have to set up on a couple of the corners of the intersection with a 3D scanner, and then we would virtually get the coordinate of the manhole instead of physically retrieving that coordinate. There is also products out there, softwares. One is called InSphere, I-N Sphere, and developed by Trimble Navigation. And it has a lot of utilities in it for urban planning and for algorithms of home density. And also technology now is helping us out with making sure that buildings are staying, there's ordinances now coming out that a building over a certain particular number of stories needs to be monitored. Well, somebody's got to be able to look at that data, analyze that data, and that's all part of geomatics.
Bob, can you maybe talk a little bit about, like, when we talk about urban areas? And I think, I mean, for me, I did this like in the 90s where there was an earthquake in my home country, and they asked us to go and measure any deflection, any tilts, deformation on some of the buildings. Do you think this is also related to urban planning? Maybe not urban planning, but if you can talk a little bit about the use of geomatics right now, different applications in deformation, in infrastructure in general, maybe.
Yeah, and the nice thing is the cost of doing this is not extravagant. When you're putting up a multi-million-dollar building and your investment to monitor it might be about $10,000. I mean, it's not and these units and sensors, they last for 15, 20 years. So, so being able to monitor that movement, and people don't realize, I put a GPS receiver on a lime silo at a mine, and I was watching it, and as the sun hit certain parts of the silo, there was movement in that building, and so, or in that silo. So, watching for movement, being able to predict it, public safety, high walls. I was just at a mine, and they're blasting. And these high walls are dangerous. And before, if they wanted information on that high wall at the mine, they'd have to get close to it. Now we can do it from a drone 400 feet in the air. So, I mean, lots of possibilities, whether it be urban, rural, either geomatics applies.
That's really very interesting. Also, if we still have some time, I would like to point out we are now beyond our Earth. So even if we are talking today about applications on the Earth, I would like maybe to take a few minutes here, if we have time, so to show you some of the interesting things we can do on other planets and on the moon. So this is part of a presentation here, and I'm just going to go quickly. So Apollo mapping. This was in the 60s. They had what we call a metric camera, and they did a lot of mapping for the moon. And then in the 2000s, they started getting these films. These were actual films. They were sent from Apollo to the Earth through capsules, and then they had the films, and they started in, I think, 2004 maybe, or 2006. They started scanning these images, and then they started doing the traditional photogrammetric application and photogrammetric mapping with the digital software thing. So this is part of the moon here. Right now, they have a lot of missions that are orbiting Mars. For example, we have HiRISE. HiRISE is called the High Resolution Imaging Science Experiment. It has a lot of images. These images are taken in a photogrammetric way. They need to do 3D models of the surface of Mars. There is something called MOLA, which is another sensor. It's like the laser scanner here. We call it the Mars Orbital Laser Altimeter. This is like Lidar on Earth. So they wanted to integrate both of these sensors to get 3D models of Mars. So a lot of applications even outside of the Earth, they have, and maybe Bob can talk a little bit about that, they have a similar system to our GPS that's orbiting, or GNSS now, and that's orbiting Mars. So It's not only the Earth, it's even Mars, the Moon, and other planets. We are doing mapping, surveying, remote sensing there.
That's excellent presentations, and thank you so much for taking the time to join us, and thank you, Dr. Lecture and Bob, for providing a great breadth of information here. So I think what we'd like to do is finish the recording, and certainly if you want more information, can you provide Dr. Lecture your contact information in the chat? So
Yes, I'm just writing my email here. I think that's the best way to get hold of me now with the pandemic. I'm not really in the office that much. So elaksher@nmsu.edu. And if you need any more information, or if you would like to learn more about geomatics, just email me and we can set a remote meeting here.
excellent. All right, thank you. Have a great night, and
Thank you.
for participating.
Thank you, everyone. Thank you.
Bye-bye.
Bye-bye.